So last class we learned about enthalpy, and we reviewed some exothermic and endothermic things. So you may remember we also talked about, I think the previous class we talked about bomb calorimetry. So let's go back to that. So the bomb calorimeter, where we have constant volume calorimetry. So we burn a sample inside of a chamber that's rigid. There's no pressure volume work that's done, and so we're capturing all of the energy that's released by the reaction as heat, and we capture that into the water that's around it. In contrast to constant volume calorimetry, we have what we did last lab, which is constant pressure calorimetry. And so we were doing stuff with delta H. We're actually talking about constant pressure calorimetry today. So that's sort of new stuff. So we talked about an enthalpy change. An enthalpy change has this delta H function. It's a state function, so it only depends on the initial and the final values. There's no what path do you take involved in that. Okay, and we came to the conclusion that delta H, or our enthalpy change, is the same as our heat at constant pressure. So building on our endothermic, exothermic delta H, we can also calculate an enthalpy change for a reaction, which is the enthalpy of the reaction or the heat of the reaction, because heat also sort of stands for H, or H also sort of stands for heat. And this is an extensive property, which makes sense if we think about burning stuff. The amount of stuff that you burn changes the amount of heat that's released. A really big bonfire is going to release a lot of heat. A really small little candle is not going to release nearly as much heat, which is why you don't have big bonfires in your house, but you have little candles in your house maybe. By convention, we calculate this delta H of the reaction based on the number of moles in the reaction. And so we can incorporate this into our stoichiometry. So for example, we've got a balanced chemical reaction for the burning of propane. We've got a delta H value for this reaction. So every mole of propane, C3H8, that we put in is going to give us 2,044 kilojoules of energy out. Likewise, if we cared about oxygen instead, we take 5 oxygens, 5 moles of oxygen, pair that up with our delta H, the negative 2,044 kilojoules, and we can make conversion factors between our moles of oxygen put in and the kilojoules, or the energy that we get out. So let's look at a very bare bones version of this. Let's say that we've got this thermochemical equation. So we've got 2 A's going to AA, and we've got a delta H of the reaction. What is the heat associated with the reaction of 6 moles of just A? So starting with our 6 moles of A, the two things that we care about in this case, we're trying to find heat. So the two things that we care about are the A, the moles of A, and the heat value. So 2 moles A turns into negative 51.0 joules, and that's going to be our conversion factor, our stoichiometry, or ratio factor. So 6 moles of A that we were given, divide by the 2 moles of A, so the moles of A cancel out, and the negative 51.0 joules goes to the top. We get joules out, and it should be negative 153 joules, which would give us C. Question? We just combined the A's together. It should probably be written as A sub 2. That's how we would normally write it if it was like individual chlorine atoms and we were combining them to form Cl2. Other questions? Cool. Okay, a little bit more of a realistic example now. So ammonia can react with oxygen in the air according to this following equation. Any guesses on whether the equation's balanced? Yeah, it's balanced. How do we know it's balanced? It's got coefficients. It's probably balanced already. We could check if we really wanted to, but I'm going to trust that it's balanced. Okay. We want to calculate the heat in kilojoules. So finding heat in kilojoules associated with the complete reaction of 155 grams of NH3. The complete reaction part here just letting us know we are using up our ammonia, our NH3. We don't have to worry about any limiting factors. So the two things we care about are what? In our chemical equation, what two things do we care about? Or are we interested in? Heat, the delta H, the heat, and what other thing? Ratio with what? Yeah, with NH3. So we're okay about NH3 and the kilojoules. So if we're starting with grams, can we do grams directly into this stoichiometry conversion factor? What unit goes with the 4NH3? Does anyone remember? What other unit goes along with it? It's moles. So we need moles. We have grams, so we'll have to convert to moles. So we've got 3 hydrogens with their molar masses. We've got 1 nitrogen with its molar mass. Add those together. Get out my calculator. Okay, so our molar mass 17.031 grams per mole for our ammonia. So we can convert from our grams of ammonia to our moles of ammonia, dividing by our molar mass. So the grams cancel, and now we can use our ratio, our 4 moles of ammonia in equals negative 906 kilojoules of energy. So 4 moles NH3, so the moles NH3 cancel. And then on the top, negative 906 kilojoules. And plop that into our calculator. And we get out negative 2,061-ish kilojoules. Questions? This is like a modification of the stoichiometry stuff that we've been doing, like grams to moles to grams. So grams to moles to energy, instead of going to moles of a different chemical. Question?
So I'm like having trouble seeing like how the things like conversion factors cross out like moles and stuff.
Okay, so we converted from grams ammonia to moles of ammonia. So the grams parts canceled out. And then we would have had left moles of ammonia. So we calculated how many moles of ammonia we had. We have this conversion factor for every 4 moles of ammonia we put in. If it reacts completely, we get out 906 kilojoules of energy.
And what does this represent?
So like if we were to burn 155 grams of ammonia, we would expect to get out, produce like 2,000 kilojoules of energy.
Which is like then absorbed by the oxygen.
it would be released into the surroundings. So it's a combustion reaction. The negative lets us know that energy is being released or emitted. It's exothermic. Other question?
Even though, like, I know you know it, if you put like 1 mole NH3 and then like 17.031 grams of NH3, it might help with us pulsing out.
Labeling the chemicals for grams and for moles.
Yeah, I know it's more work. Like,
Sure. Yeah, we can do that.
that might.
Okay. I just don't do it partly because I'm a little lazy about doing that.
It's okay. I did it otherwise. I would just
Cool. All right. Another example, perfect opportunity. What mass of butane in grams is necessary to produce this much kilojoules of heat, 1,500 kilojoules of heat? And then a related question, what mass of CO2 is produced at the same time? So we're using some energy. We're also figuring out a mass of CO2. So what mass of butane is used and what mass of CO2 is produced. And the number that we're given is kilojoules of heat. So if we're given heat, we're starting with heat. Where can we go from heat? So we've got kilojoules. What's the heat value that we're given in the balanced reaction? Also in kilojoules, so it's convenient to be in kilojoules. So that's one of the things that we care about because we're given a heat value. What's one of the other chemicals that we're interested in? What are we trying to find? Butane. So butane is going to be the C4H10. So 1 mole C4H10, that's our butane. If we burn that, we'll get out 2,658 kilojoules. So this is our conversion factor between kilojoules and moles of butane. So we can plug this in. We put the kilojoules on the bottom so they cancel. The 1 mole of butane goes on top. Our molar mass for butane is 58.124 grams. So we got rid of the kilojoules in our first step. We converted to moles of butane. If we multiply by our molar mass, the grams of butane's on top, the moles of butane on the bottom. So that'll get us out grams of butane. So kind of working the opposite direction of the previous problem. And then we also have to, oh, and I made an oopsie. I got negative 32.8 grams C4H10. What's wrong about that? It's negative. We can't have negative grams, right? So the oopsie comes from produce 1.5 times 10 to the 3. So this was a negative number. It doesn't really affect our calculation except that we should know that we're supposed to get out a positive number. So if we added a negative in front of our energy to start with, we would end up with a positive number at the end. Or if we just knew that we can't have negative grams, and if we were thinking about it in the moment, we switched it to a positive number, that would also fix our issue. Okay, so keeping in mind our negative, we also wanted to know what mass of CO2 is produced. And so we can go from the kilojoules to CO2 instead. We'll do that in Orange Go Giants. So our conversion factor, our ratio, is now negative 2,658 kilojoules, the same amount of energy, but this corresponds to 4 moles of CO2 being produced. So 4 moles of CO2 produced for every 2,658 kilojoules of energy that was also produced. And we would need the molar mass of CO2, and I think 44 is close enough if my brain is being nice. Just for expediency, I'm not going to calculate it. Okay, so our kilojoules, we do our conversion between kilojoules and moles of CO2. So our kilojoules get canceled out. We multiplied by our approximate molar mass for CO2. So the moles of CO2 also cancel out. And we would be left with an amount of grams of CO2. Any delta H questions? Yes.
Why is it negative 44 grams?
Oh, sorry, that's approximately 44.
Oh, okay.
I just didn't make it wiggly enough.
It's okay.
Very wiggly now. Okay, so as teased, constant pressure calorimetry, which we did on Tuesday, the coffee cup calorimetry. It's a cheap and effective way of doing calorimetry. You can also buy, like, there's more advanced versions that are also basically just coffee cups. So we just use the coffee cups because it does a good enough job. So for coffee cup calorimetry, we had 2 nested foam cups just for extra insulation. It's open to the atmosphere. We didn't do any like sealing it up. It probably also wouldn't withstand any pressure. So it's open to the atmosphere, which makes it a constant pressure environment. So the heat that was produced in our solution when we did a reaction, or in the case of our calorimetry, we were just exchanging heat. In this case, we are doing a reaction, so the heat produced by our solution is equal to the mass of the solution times the specific heat value of the solution and our change in temperature. That's our solution, sorry. Our reaction is producing whatever heat our solution absorbs. So if our temperature of our solution goes up because of a reaction occurring, that heat we would expect to have come from a reaction. And so that reaction heat that it's produced is going to be our QP, our heat at constant pressure, which is approximately the same as our change in enthalpy of the reaction. So this can do like an okay job of estimating our delta H for a reaction. When we do these reactions, our delta H needs to be per mole, and so we need to divide by the moles that we reacted, which we'll see in this next problem. Okay, so we react hydrochloric acid and silver nitrate, which precipitates silver chloride, and we also get nitric acid out. If we mix 50 milliliters of 0.1 molar silver nitrate and 50 milliliters of 0.1 molar hydrochloric acid, in our calorimeter, so we're adding in equal mole amounts of our hydrochloric and our silver nitrate, our temperature changes. It goes up a little bit. So we're starting to get a lot of variables. Let's go ahead and write some of these out on the side. So for our temperature, our initial temperature is the lower value from 23.4. So 23.40 degrees Celsius is our initial temperature for our solution. And it's raised to a final temperature of 24.21 degrees Celsius. We want to calculate the delta H of the reaction. So for starters, we need to figure out how much heat was produced. So how much heat was produced? We can measure the amount of heat because we know the amount of water, the amount of solution, and we know that the solution is basically water. We're told to use a C value of 4.18 joules per gram degree Celsius. And we have a change in temperature. So we've got everything that we need to solve for Q equals MC delta T. If we're using the same nomenclature that we were using, if we're using the same terms as we were using on the previous slide, this would be finding our Q of solution. So what amount of energy did our water absorb, or our solution absorb? Any questions so far? So to find the mass of our solution, we need to look at what we added. So we mixed together 50 milliliters of one solution, 50 milliliters of another solution. So what's our total volume of our solution? It's 50 plus 50, so 100 milliliters of solution. And we were provided a density value for our solution. So our density value can help us get to our mass of solution. Our density value is 1 gram per milliliter. So for every 1 milliliter, we have 1 gram of solution. So multiplying by 1 gram per milliliter, we get out 100 grams of solution. So this 100 grams of solution is our mass value. We were also provided a C value. So we've got the C value. Can we find a delta T? Yes, we can find a delta T because we were given two temperature values. We're giving a final temperature and an initial temperature. So we can use those to calculate our delta T. So the Q of the solution, the heat absorbed by the solution, 100 grams times 4.18 joules per gram degree Celsius times our final temperature of 24.21 minus our initial temperature of 23.40 degrees Celsius. Our grams will cancel. Our degrees Celsius will also cancel. And we will get a Q value of 338.58 joules. Is this our delta H of the reaction? Any guesses? It should be negative. So the value that we found is our Q of solution. So that was how much energy went into our solution. That energy must have left or been produced by our reaction. So Q reaction is going to be the negative Q solution. So negative 338.58 joules is our Q of, or our heat produced by the reaction. If we did this again and we used different amounts, how would we figure out if we got the right amount of heat produced? Huh? Stoichiometry? Is that what you're saying? Yes. There's a part of the stoichiometry that we're missing. So if we refer back to our previous slide, to get the delta H reaction per mole, we need to divide by the moles that reacted. This lets us relate it to different mole amounts that we used. So our last step is an important step, little step. We need to divide by the amount of moles that we used of whichever of our reactants. They're all 1-to-1, so it doesn't matter which one we use. So this is the last little step where you're most likely to forget. So we have to remember what molarity is. Molarity is moles over liters. So we can calculate the moles of either of our reactants. Because we've got the molarity, we've also got the milliliters, which we can convert to liters. So 0.0500 liters. If we rearrange to solve for moles, we're multiplying molarity by liters. So our moles is going to be something like this. I never have enough room. So 0.005 with some zeros for significant figures after it. So this amount of joules was produced by this 0.005 moles. If we divide by that 0.005 moles, this works for either our hydrochloric acid or our silver nitrate, then we get, pick the wrong thing, 67,716-ish joules per mole, which we would probably convert to kilojoules. It didn't tell us specifically. Questions? Yes?
So we don't have to convert
We don't have to convert the temperature
the temperature to Kelvin.
to Kelvin In this case, because we're doing a change in temperature, the change in temperature for degrees Celsius and Kelvin is the same because the units are the same, they're just shifted. If you wanted to see that that works, you could convert it from Celsius to Kelvin and then subtract it, and you should get the same delta T. Other questions? Yes.
If this was on a test, you wouldn't be expected to like find it per mole. It just says delta H of reaction. Right? It would say like delta H of reaction per mole.
I probably would not tell you that it's per mole. I would expect you to get it as a per mole. Because we're looking for it for the overall reaction. If I just asked you for the heat that was produced by the reaction, then you wouldn't have to do it on a per mole, because that we produced an actual amount. But for applying this to other circumstances, other batches, other reactions, like different amounts, we would need this per mole amount to be able to figure out if we did it correctly or something went wrong. So that's part of why I pointed it out on the, we'll give it a little extra attention. Because in all of our other examples before, right, these delta H of reactions, this is secretly for one coefficient number of moles for each of our reactants and products.
So for that one, it's like, that's per 1 mole of O2? Or
It's per the coefficient of moles of O2. So 13 over 2 moles of O2. Yeah. Okay, a little bit of testing our concepts. We do the same reaction with exactly the same amount of reactants. We do it in a bomb calorimeter, that's the sealed one. We also do it in the coffee cup calorimeter, the one that's open to the atmosphere. In one of the calorimeters, the Q of the reaction, the heat produced by the reaction, is measured at negative 12.5 kilojoules. In the other, it's negative 11.8 kilojoules. Which of these values was obtained in the bomb calorimeter? We would assume that the reaction has a positive delta V in the coffee cup calorimeter. What's different about the bomb calorimeter versus the coffee cup calorimeter? One's constant volume, the other's constant pressure. Why does the volume or pressure matter? Yeah.
Does it affect the rate of reaction?
It could possibly affect the rate of the reaction, but we completed both of the reactions in this case, so that wouldn't be a factor here. Something specifically about the pressure or the volume? No, it's not because they're inverse. Is there another place other than heat that our energy could go? Is there another way that we could use our energy? Think about you sitting around at home. If you're just sitting around at home, you're generating heat. Is there something you can do other than sitting around at home? Chores, which would be what? Or a job, which would be work. Is there a type of work that involves pressure or volume? Remembering anything about that? Okay, so the thing that we're looking for, we got very close, is pressure volume work. So in one of these situations, we can do pressure volume work. So we can lose some of our energy because of our reactant or our gas or other things expanding. That's what this assume the positive delta V in the coffee cup calorimeter. There's a negative sign there. So in one of these scenarios, our reaction can do pressure volume work. It can expand. In the other, it can't. And so all of its energy is trapped as heat. So in the bomb calorimeter, no hyphen. In the bomb calorimeter, all energy goes to heat. Because we've confined it to a space that's not able to expand, all of its work, all of its energy, it's not work, all of its energy goes into heat. So we capture all of its energy as heat. In coffee cup calorimetry, some energy is lost to work. Pressure volume work. So a little bit of our energy goes towards expanding our gas or just expansion generally. That is work. So which of these values was obtained in the bomb calorimeter? We didn't lose any energy to work. Does that mean that we have more energy for heat or less energy for heat? More energy for heat. And so the correct answer would be A. Yeah, question?
So on the last one, where we did the kilojoules over mole.
Yes.
So let's say that like one of the coefficients was 2, because all of them are 1. But like let's say one of them was 2. Like what would be correct to divide it by like joules? Because one of them would be half the amount of the other one. Like if you divide it by 2 moles.
Right.
So is it like it's not just per mole of some like arbitrary thing, it's per mole of a certain like compound that is being reacted?
Yeah, if they weren't 1-to-1, I think it would be per mole coefficient times the number of.
Wait, which is
So the coefficients would come into play. But if one of them was 2 and the other one was 1, I would just divide by the one that was 1. We would also have to use twice as much of the one that has a coefficient of 2. We can maybe find an example of that during lab. Okay. So we can also do some other stuff with change in enthalpy of a reaction. So the change in enthalpy is for a particular reaction. It's for the reaction as written. If we adjust our reaction in any number of ways, then our enthalpy of the reaction, our change in enthalpy, is also going to change. So there's 3 primary things that we're going to do. 2 of them are here. The next one we'll see on the following slide. So if a chemical equation is multiplied by some factor, for example, if we double the coefficients, then our change in enthalpy of the reaction is also multiplied by the same factor. So our delta H would also double. And it doesn't have to be nice, neat doubling or halving. It can be any factor that we want to put in front of it. Usually it's going to be something like multiply by 2 or 3 or divide by 2 or 3. So an example, if we've got A plus 2B goes to C as a reaction, and we've got an enthalpy for that reaction. If we double all the coefficients, so it's now 2A, instead of 2B it's 4B, instead of 1C it's 2C. If we double all those coefficients, we use twice the amount of our reaction, of our reactants, and so we would expect that our enthalpy change is also doubled. If we flip the products and the reactants. So if we run the reaction backwards, if it's reversed, then our delta H of the reaction changes sign. So if it was positive, it goes to a negative. If it was negative, it goes to a positive. So looking at that same, A plus 2B goes to C, that has some delta H value. If we flip it and we take C and turn it back into A plus 2B, if we got energy out to make C, we would have to put energy in to take C to make it back into A and 2B. So our new delta H value would be the negative of our initial delta H. And then the third way that we can mess around with our delta H is with Hess's law. So Hess's law, in case the bolding wasn't enough, I'm boxing it in. So Hess's law states that if a chemical equation can be expressed as a sum of steps, so if we can do an individual reactions that add up to the overall reaction we want, then the delta H of the overall reaction is what we'd get if we added up the heat of reaction for each step. So looking at two different reactions, we've got A plus 2B goes to C. C is going to go in, turn into 2D. So we're kind of like stringing together a series of steps. So it would make sense that the energy from the first step, if we add that to a second step, if we just add those steps up, then that should also be our delta H. So on the right, we've got a visual of what that would look like. So we've got our initial reaction, A plus 2B, it goes to C. Some amount of enthalpy is released. And then from C, it turns into 2D, and there's a different enthalpy value for that. So if we go through both of those two steps, it should be the same as adding up the enthalpy values. So we can multiply all of our coefficients to change our delta H. We can flip the left and the right to reverse or negative our delta H. And we can also add up delta H. Our left and right sides need to cancel out when we're doing these additions. We'll have some examples of this as well. So why this is important, why this is helpful, is that some reactions are difficult to measure, or maybe nearly impossible to measure, but we can measure individual steps that would lead up to that total reaction. And so this lets us take some delta H values that we know for reactions that we know and manipulate them, change their coefficients, multiply them to make them bigger, divide them to make them smaller, flip them left and right, and then add them together to get the overall reaction that we want. So it lets us sort of like indirectly get to the H value that we want, delta H value. So some examples. Let's say that we've got this equation where we're reacting 2A, where A is some chemical. We're reacting that with B, a different chemical, and it produces C, some third chemical. And our delta H of the reaction is 122 joules. What would be delta H be for this reaction? 2C going to 4A and 2B. So think about, what did we change? How did we change our initial reaction to get to this reaction? What's one thing that we changed? What's one transformation that we did? We went from 2 to 4 for our moles. So we doubled the moles. So we multiplied by 2. So 2A plus B to C has a delta H value of 122 joules, and we went to 4A plus 2B goes to 2C. That's the multiplying, the doubling part. How does that change our delta H? It's doubled. So now instead of 122, joules, it's 244 joules. So we've got this new 4a plus 2b goes to 2c, which is different from 2c to 4a plus 2b. What other change did we do? We flipped it left and right. So flip left and right, or flipping our reactants and our products, we're running the reaction in reverse. So how is that going to change our delta H value? It's going to be negative. So negative 244 joules. So it flips from being positive to being negative. So the correct answer here should be D. All right, now trying it out with some Hess's law, so adding reactions together. This is an example of what you might see as like a free response question on an exam. So we want to find the delta H of the reaction for this reaction. So we've got N2O plus NO2 goes to 3NO. And we've got some reactions with known delta H values. So our goal is to figure out how we can rearrange these reactions so that we get this reaction out at the end. So I would recommend, let's see if there's any chemicals that only show up in one reaction, and then we can set those up to start with. So for example, the N2O only shows up in this last reaction. N2O is on the left side, so in this reaction we need N2O to be on the left side as well. Let's go ahead and pull that out so that we can start using it. And our delta H, negative 163.2 kilojoules. Is this N2O the same as the N2O that's in our desired equation? It's the same N2O, but does it match exactly? It doesn't. What do we need to do to get them to match? We would need to divide by 1/2, right? And then that would turn into N2O goes to N2 plus 1/2 O2. What happens to our delta H when we do that? It also gets halved. So negative 81.6 kilojoules. Okay, so we've got this part, we've got the N2O part lined up. We've got that ready to go. And to save space, I'm going to shrink that and set it aside. Okay, so we've got the N2O figured out. We've got that part solved. We also need NO2. Which of our equations, which of our reactions, the first, second, or third one, has NO2 in it? It's the first one, right? We've got NO2 in our first reaction, but it's on the product side. Is that where we need it to be? What side should NO2 be on in our reaction? It should be on the reactant side. It's currently on the product side, so we need to flip it. So 2NO plus O2 goes to 2NO2. just rewriting it out. Okay, so we need to flip it. So let's flip it. So 2NO2 goes to 2NO plus O2. How does our delta H change when we flip it? Yeah, it flips to positive. So now it's 113.1 kilojoules. Does our NO2 that we have in our reaction down here match up? Is it exactly the same as our NO2 in our desired equation? It's not, right? So again, we have to have it. So this is NO2 going to NO plus 1/2 O2. And our delta H gets cut in half again. And I think that's the correct math for cutting it in half. Okay, so now we've got our NO2 figured out. That's not going to get everything. So we'll set that aside. And then the last thing that we need to work out is our NO. So let's look at what we've got so far. So we've got N2O going to N2 plus 1/2 O2. And we've also got this NO2 going to NO plus 1/2 O2. If we add these two together, we've got N2O plus NO2 on the left side, which is perfect. And then on the right side, we've got N2 plus NO plus O2. The 1/2 O2s add up. Our left side here is good, it's perfect. The right side, on the other hand, we've got one NO, we need 3 NOs. So we're close there, but we have an unnecessary N2NO2. Can we use our third equation to cancel these out? How many more NOs do we need on the product side to get to 3? 2, right? Which is what we have in this middle equation. So if we add N2 plus O2 and 2NO, anything that's duplicated on the left and the right we can get rid of. So that's going to be the N2 and the O2. And then we would add up the NOs on the right side, so we would end up with 3 NOs. And since we didn't change this one at all, our delta H would remain as written. So then our delta H for the reaction is the delta H for these two reactions that we added, and we had calculated those previously, plus the third one. So our delta H of the reaction is negative 81.6 kilojoules. Plus 56.55 kilojoules. Plus 182.6 kilojoules. So that'll shake out to about 157.6 kilojoules for that reaction. Questions about any of those parts? Yes? The last step, the green one?
Yes.
So the N2 plus O2, we had from adding our other ones up to get our reactants correct. Right, we added those together. We had unnecessary N2 and O2 on the right side. So we added these up. Anything that's duplicated, anything that's on the left and the right, we can cancel out. So we had one N2 on the left side, we had an N2 on the right side, we had an O2 on the left side and O2 on the right side, so those cancel out. And then we're left with the two NO. There's also one NO over here. If we wanted to think about it as multiple steps, this reaction, our green reaction, says that N2 and O2 will turn into 2NO. So we've got N2 plus O2, right? So those would turn into 2NO. So sort of like stringing together a series of steps, we're transforming the N2 and the O2 into the 2NO. Other questions? Okay, I will give you some time to work on one. And feel free to discuss with your neighbor, and then we'll go over it real quick together. So to get these two reactions to add up to 3H2 plus O3 ozone plus goes to 3H2O, again, we probably want to be looking at which equations do we need to get something that's on the left side or the right side. I usually just start with the first thing. So the H2, we've got one reaction with H2, and it's this first reaction. We need 3H2. So we're going to have to do some sort of multiplication, some sort of change to get up to 3H2 from 2H2. So to do this change, we're going to multiply everything by 1.5 or 3 halves, 1.5. That'll turn the 2 into 3. It also puts, I'm going to write 3 halves just to save space in front of our O2. It'll also turn this 2H2O into 3H2O. So now that conveniently, we've got our H2 and our H2O matched up. And the way that that's going to change our delta H is that it's also getting multiplied by 1.5. We didn't do any flipping, just left it as it is, multiplied by 1.5. And then to get our O3, our ozone, we've got ozone in our second equation, but it's on the wrong side. So we're going to need to flip sides so that it's no longer a product, it's a reactant. And we've also got 2 ozones in this reaction, and we need to get it down to 1. So we're going to have to do a couple of things. We're going to have to flip it. And we're going to have to cut it in half. And that means that we're going to do the same thing to our delta H. So we're going to flip it, we're going to multiply it by a negative, and we're going to cut it in half. Okay, so let's rewrite these after we make those transformations. Our 3H2, our 3 halves O2, our 3H2O for our top equation. For our bottom equation, we flipped it left and right and divided by 2. So on the left side, we would have O3. And on the right side, we've got this 3O2 now divided by 2, so it's 3 halves. O2. And then to get the oxygens to cancel, we've got 3 halves O2 on the reactant side, we've got 3 halves O2 on the product side. So we can cross those out. If we're thinking about it stepwise, our O3 would turn into O2s, which then reacts and goes on to H2O. So we can omit the O2 part, sort of like weaving it in. So our final would be 3H2 plus O3 goes to 3H2O. That was the goal. And then we have to add up our delta H's with the changes that we made to them. So our delta H is negative 483.6 kilojoules, and that was times 1.5. So that's our first delta H value. Our second delta H value we multiplied by negative 1/2. So 285.4 kilojoules times negative 1/2. You could assess those before you add them together, but I am doing it all at once so it's less stuff to put in the calculator, or less writing overall for me. Any questions about the process? Okay, we will sort of tease the next section because we don't really have time to finish it. So we can also do delta H of a reaction, or change in enthalpy of a reaction, from what are called standard enthalpies of formation. So we can measure them experimentally via calorimetry or by inference, so like adding up equations. We can also use a table of standard enthalpies of formation. And one of the nice things about these being calculated as a change in enthalpy, it's just the total difference in enthalpy. So we can change a reference state. So we can measure changes in altitude relative to sea level, for example. Sea level is a convenient measuring place since it's about the same all over the world. It would be unfortunate if our altitude was measured relative to like Salt Lake City, Utah, because then we would have to like compare everything to Salt Lake City, Utah, and that's not really an easy thing to do, especially if you live on the coast, since the sea is right there. The sea is right there. The ocean is right there. So we can measure changes in enthalpy relative to enthalpies of pure elements in their standard states, because pure elements in their standard states is a little bit easier to get just kind of generally around the world. And so that's what we're setting as our baseline. So we have to first define standard states. And the way that we define standard states is so that it's relatively easy and convenient. So the numbers are not terribly difficult, I think, to remember. So the standard state this may be giving you some flashbacks to standard temperature and pressure. It's not exactly the same as standard temperature and pressure, but that's the sort of standard that we're talking about. So for a gas, we're talking about the pure gas at exactly 1 atmosphere of pressure. 1 atmosphere, very convenient unit of measurement. So we're just 1 atmosphere. If we're using a liquid or a solid, it's the pure substance in its most stable form at, again, 1 atmosphere of pressure, and whatever our temperature of interest is, usually 25 degrees Celsius or 298 Kelvin. That's like the room temperature. If we're doing a substance that's in solution, then we're defining the concentration as 1 molar. Usually your table will already have temperature taken into consideration. So this is kind of more like I might test you for a definition for these. Like what is the standard state for a gas? What's the standard state for a substance in a solution? Something like that. Our standard enthalpy change, standard is denoted by this degree sign. And then the enthalpy change part is the same. The standard enthalpy change is when all of the reactants and products are in their standard states. And again, that degree sign indicates standard states. Sometimes you'll also see it as a different symbol called a plimsoll, apparently, which is used in like ships. It's this thing. So these are enthalpy changes when reactants and products are in their standard states. Standard enthalpy of formation, we're adding in this little F for formation. So if we're getting in formation, the enthalpy change for forming 1 mole of a pure compound. So we're forming 1 mole. So the product is 1 mole. And this is from its constituent elements. We can also call this the standard heat of formation, since the H sort of stands for heat. It's not exactly the same as heat. Our elements need to be in their standard states. For a pure element in its standard state, the change in enthalpy, the standard change in enthalpy of formation is 0 kilojoules per mole. That's the state that it's normally in. That's the state that it wants to be in. So if we're trying to get it into that state, you don't have to do anything. There's no enthalpy change. So that's always defined as 0. Enthalpy changes are measured relative to the elements in their standard states. So we're setting those as our baseline 0 state. And part of the reason that we don't have time to get into all of it is because we've got a couple of tables and there's more calculation stuff. It's going to sort of mirror what we were doing with Hess's law, sort of. It's just a little bit more complicated because there's a table to look stuff up in, and you have to make sure you find the right entry in the table. Otherwise, though, it's about the same, I think, level of difficulty as the Hess's law stuff. Questions before we wrap up? Okay, then we'll stop there.